So good morning everyone. I welcome you all in Sapience education. So today I am going to discuss about all this topic. So topics which will be covered is your relationship between stress and strain. Earlier I have already discussed about stress and strain in previous video. That is part 1 video, right? Now today I am also going to discuss about Hooke's law. Next is your modulus of elasticity and types of modulus of elasticity. So from here figure you can understand the behavior of a material. What is there is a material, and if it is being loaded, then material shape is changing from time to time, and due to this change in a shape, what are the properties has been changed in the material. So we will discuss it in a details. So we will also discuss about Hooke's law and Hooke's law, yield point and all. Okay, so step by step I will go for this. Now, first of all, you need to understand what is actually elastic limit. It is the maximum stress a material can withstand before the permanent deformation. So, what do you mean by permanent deformation? Let us consider a material is like this, okay? And this type of material, see here in figure, this type of material is being pulled from both the sides. So, what will happen? Its size will change. Definitely, its size will become longer and its thickness will become less. So what will happen if you release it, if you leave this, so what will happen, it will come again in the same shape. But as soon as you will apply a force more and more, what will happen, a time will come, then it will become permanent deformation. After that it won't regain its original shape and size. So till here it regain its shape and size. When you leave, when you just remove the force, so what will happen, it will regain into this shape, and this is called the elastic limit. But as soon as you have crossed the limit of applying a force, so what will happen, it will try to become very thin, and it won't be able to regain itself. And the limit is known as elastic limit. I hope you have all understood now about elastic limit. Okay, so see here, from the figure you can understood that how material is being pulled from the very heavy load, and load is being applied from at the top and above, and we can study from the electronics panels the behavior of material. So let us go for discussion about Hooke's law. So what is Hooke's law? Hooke's law, stress is directly proportional to strain within the elastic limit for a body. So stress, before you know what is stress, just I have given discussion. I have given discussion about stress, that is equal to force applied by area. It is known as stress. And I have also discussed about strain, that is equal to change in length by original length, or change in any area by original area, change in radius by original radius, or whatever, any change in configuration by original configuration is known as strain. So I hope you have understood this stress and strain. Now according to this, what is happening, Hooke's law gives a property of a material that stress is directly proportional to strain, right, within the elastic limit. Just now I have told you what is elastic limit, right? So elastic limit is the limit up to which permanent deformation won't stress, it is the maximum stress of a material can withstand before the permanent deformation, right? Now Hooke's law, stress is directly proportional to strain within elastic limit. So that's, for example, there is a elastic limit like this, right? And up to this, what is happened, the more stress is directly proportional to strain. If you increase stress 2 times, so strain will also increase 2 times. For example, earlier stress was 10 Newton per meter square, and strain become 1 meter. So if you increase it by 2 times, for example 20 Newton per meter, so what will meter square, so what will be the strain? See, this is your stress and this is your strain. See how this is behaving. So this will be also 2 meter, right? It means that they both are directly proportional. But the thing is that they have told that there is a limit, and this limit is called elastic limit. It is the material property. So stress is equal to E into strain. This is your constant of proportionality. This is your constant of proportionality. Okay. constant of proportionality, and it is called modulus of elasticity. And the zone is called elastic limit. This zone up to which it is called elastic limit. Okay. So I hope you have understood now Hooke's law. Whenever you explain in an exam Hooke's law, just try to write or draw the diagram so that it will be very much easier. See here, in y-axis it is your stress, and in x-axis it is your strain, right? Now I will discuss about stress strain graph in more details. Okay. So see here, this is a simple graph of stress and strain. So how a metal behaves? See here, metal behaves. So as soon as you increase the stress, so material strain. See here, lower one is your strain. Okay. See here, lower one is your strain, right? So as soon as you will increase the stress, so strain will be also increase. Okay. Strain will also increase. Again you try to see here. Let us see this graph. See here, up to this you have increased the stress, so due to this what happened, strain is also increased, and this is known as, this is up to this what is happening, proportional is, it is your proportional limit. So OA, stress is directly proportional to strain, and A is a proportional limit. Up to A it will follow direct, stress and strain are directly proportional up to A. That's why the point A is known as proportionality limit. The point O is known as proportionality limit. I hope you have understood now, because up to this stress is directly proportional to strain. So you can directly write like this, up to A, stress is directly proportional to, stress is directly proportional to strain, proportional to strain. I hope you have understood now, right? And proportional limits, so up to OA proportionality limit, and Hooke's law is followed here. Hooke's law is followed without within the elastic limit, then the limit, that limit is known as OA, right? So up to OA only Hooke's law is followed. After that Hooke's law not followed. Why? Because it's here you can see it appears from a graph that stress is not directly proportional to strain. Okay. So I hope you have understood the part OA. Now I will go for next part, that is B. Okay. So what is B now? B. What is B? So this is your yield point. This is your B is your yield point. As up to B, body will regain original state. See here, very important, minute changes are there. See here, up to A, what is happening? Stress is directly proportional to strain. Okay. But after A to B, stress does not follow the these rules. That is, stress is not proportional to strain. But the thing is that up to B, when material reaches up to B, after that it will again regain. So up to B, body will regain its original length after the deformation has been removed, right? That is, elastic property will be shown up to yield point only. So up to B, Hooke's law is not followed. Remember, Hooke's law is only followed up to proportionality limit. But what is happening here? But up to B, elasticity, material has elastic property up to B only. Why elastic property? Because elastic property means what? Body will regain its shape and size originally when a force is being removed. So up to this, up to B, what is happening here? Up to B, try to understand, up to B what is happening? Up to B, up to this point, when you remove a force, for example, you have applied a force in this material above and below and above. So what is happening? It is deformed, so it become thinner. Up to B you have applied. Up to B means what? Stress sigma y you have applied. And after your removal of stress, what is happening? It become again its original shape and size. And that's why it is known as yield point. That's why it is known as yield point. I hope you have understood now. Yield point, up to yield point, body will regain, body will show the elastic property, right? Yield strength of the material, and this is called the yield strength of material, the strength up to which body will regain its original shape, right? For example, my body is this is my body, and which has length 1 meter. After applying force, what happened? Up to stress up to B, that is yield strength I have applied. For example, yield strength is your 50 newton 50 newton per meter. After that, yield strength is not there. So up to 15 newton per meter, when you have applied, then what happened? It become 1.3 meter. As soon as you have removed this strength, that is stress, that force, amount of force for a sigma y, then what is happening? Again it become 1 meter. So that's why it is known as yield strength. I hope yield strength is okay now. You have understood yield strength, and you have also understood yield point, right? Now I will talk about BD. So within BD, body does not regain its original dimension. After you apply stress after B, so what will happen? If a body size is my 1 meter, and when I have applied after B, suppose I have applied some stress, our yield strength stress was 50 Newton per meter square. So as soon as I have applied 55 Newton per meter square, so its size changes from 1.1 to 1.5 meter. So again it won't regain when you remove, after removal of force. See here, after you remove a force, so what is happening? So its size become 1.2 meter. So what does this means? It does not regain its original shape or original dimension after removal of force. Then the material is also said to be permanent set. So suppose this is the material dimension, you have applied a force. So what is happening? After you apply the force, so what will happen? Its size will become more long. But as you remove the force, so what will happen? It will try to shrink, but it won't be like suppose it is your 1 meter, it is your 1.5 meter. So again, after removal of a force, you see that 1.2 meter it is. It means that material is said to be permanent set. It won't go for its original size. So this is called permanent set, right? I hope you have understood now. Now deformation is said to be plastic deformation. I have already discussed about plastic deformation. So from B to D, when you apply a stress of from B to BD, that is yield to ultimate strength. So up to this, the deformation is called plastic deformation. So whenever question will be asked, so you have to give up area. This area of plastic deformation is happening here. This area is your plastic deformation area, and up to A, this area is your Hooke's law zone. Up to B, what is happening? Elastic zone. Up to B, elastic zone. So there are several types of zones you will come across this. Okay, so I hope you have understood now. So plastic zone, it is your plastic zone, it is your elastic zone, and proportionality, that is Hooke's zone. Hooke's law will follow here only. So I hope you have understood this now. Now stress corresponding to the D is called a strength. See here, D, when a material reach at point D, so what is happened? The stress corresponding to this point is known as ultimate strength. Beyond D, if stress is reduced, then also there will be a deformation. See here, when suppose up to this, what is happening? You have applied ultimate strength of 600 or 60 Newton per meter square. Now as soon as you, after this, what is happening here? If you apply only 55 Newton Newton per meter square, or 50 Newton per meter square, then also there will be change in a strength. There will be a strain. See here, strain is increasing. Beyond D, even if the stress is reduced, then also there will be a deformation. And the point E is called fracture point. After the material, this material will break. So the point E is known as fracture point. I hope you have understood now. So this is a fracture point. So this is a way how to read the graph. Okay, so again I am making your some revision here. Okay, see, first of all, you need to understand here. See, this OA, this zone is Hooke's zone, where stress is directly proportional to strain. Where stress is directly proportional to strain. Now after that, when we come across that B zone, so what is happening? B zone. So B zone is your elastic zone. What do you mean by elastic? Elastic zone, it means that up to this body will regain its shape and size. But as soon as this zone from B to D comes, it means that it is your plastic zone. Why I am talking about plastic zone? Because it unable to regain its shape and size in this zone. And after this D and E is known as fracture point. After D to E, what will happen? Material will try to break, or definitely it will break at a point E, right? So I hope you have understood this graph in a proper way. Now if D and B, very important, if D and if D and E are closed material, is said to be brittle. For example, glass. For glass material, D and E will be very close. Any brittle material, so which can easily break it down. So for that material, D and E will be same point. Now, if they are far, then material is said to be ductile. See here, the more D and E point is far, if D and E is larger, then we can directly say from the figure that material is ductile. Material is ductile. Ductile means if you there is a wire and it can be drawn for a long wire without breaking, that is ductility. So this is a opposite of brittle. So brittle means easily breakable. Ductile means won't breakable. It's like wire. If you stretch a wire, so it won't break easily. Okay, so this type of property is known as ductility property. This type of property is known as ductility property, right? Now let's go for so again I hope you have understood the graph like this. So this is, again, if you want to draw like this graph, so just you draw, this is your stress and this is your strength, and just you draw like this straight line. Because why I'm talking about a stress line? Because it is directly proportional. So up to this this point is known as, you know well, I think you know well. After this there is a elastic property, and after this point, suppose this is your A, this is your B, and after this what will happen? After this, see here, after this it will curve like this. So suppose this is your ultimate tensile strength, this is a point D, and this is your fracture point E. Okay, so this is your Hooke's zone, Hooke's law zone. Hooke's law will be followed. Hooke's law will be followed. Okay. Now after this, what is happening? After this, see here. After this, what is happening? See here. This zone is your elastic zone. Why elastic zone? Because what is happening here? Body will again come to the its original shape and size. So if you take about if you take another next point, that is any point between B and D. So suppose you have taken C. So this is your plastic region. This total region is known as plastic region. Okay. So I hope you have understood now. You can understood that this is your Hooke zone, this is your elastic zone, this is your plastic up to D, it is your plastic region, and after this what is happening? Fracture point, it is your fracture point. So these things you must remember. Okay, fracture point. So I hope you have understood now. So for any exam, you there will be a lots of question regarding this graph. So that's why I have focused on this graph. Okay. So now some material does not obey Hooke's law. So many, you know that every year in nature, it is a property that no one will behave similar like different. There will be definitely an exception. So some of the material does not obey Hooke's law for many reasons, and there is no well-defined plastic region, and it is called elastomers. So see here, stress strain. So stress strain of a curve of a elastic tissue. See, take elastic tissue of aorta, the large tube of a vessel carrying a blood from heart. So when you apply very stress, zero stress, very low stress also, but it won't show the Hooke's law property. So this type of things is known as elastomers. These type of things are known as elastomers. It is type of material is not well defined plastic region, no well defined plastic region. See here, if it would be see our plastic region would be like this and like this and this is your plastic region, but in this no well defined is there. So in this type of material is known as elastomers. I hope you have understood now. Now I hope you have understood now. Now let's discuss about modulus of elasticity. Okay, it is defined as the ratio of stress corresponding to strain. It is defined as the ratio of stress corresponding to strain is known as modulus of elasticity. As in a previous discussion, as we know that stress is directly proportional to strain. So try to remember this in both symbol. This is the symbol of stress and this is the symbol of strain. So stress is directly proportional to strain. So if you remove proportionality constant, so there will be some constant, and this is called what? And this constant is called modulus of elasticity. So modulus of elasticity can be defined as stress by strain only, right? So I hope you have understood now. What is the unit of a modulus of elasticity? So as you know that stress has what unit? Stress is means what? Force by area. So force is your Newton by area, that is meter square. What is the unit of strain? Strain is your change in length by original length. So length that is meter will cancel out, so no dimension at all. So strain has no dimension. Strain has no dimension, right? So if you want to find a unit of a modulus of elasticity, so stress as a Newton by meter square divided by no unit. If there is no unit, so just you can write that it has a unit of a Newton per meter square. Okay. Now its value depends upon the nature of a body, of a material, and manner in which the body is being deformed. Okay, so it not only depends upon material of the body but also the how body is deformed. For example, if body is being stretched like this upward and downward, so it is different thing. So if body is cut like this, so it is different thing. If body is being compressed from up and down, so there will be a different values of modulus of elasticity, but it depends upon the material. Basically it depends upon the material as well as how it is being deformed. Okay, now there are several types of modulus of elasticity at all. So first I am talking about modulus of elasticity, that is your young modulus of elasticity. What is young modulus of elasticity? It is represented by y. So it is the ratio of normal stress to the longitudinal stress. So I hope you have understood now. What is longitudinal strain and what is your normal strain? In unit is your Newton per meter square. See here, try to understand what is actually a normal stress. See here, normally I have already discussed this thing in a previous video, that whenever a force is being applied like this and the area of cross section is perpendicular to this force, then the internally there is a deforming force at all. So the normal stress is what? In deforming force per unit area, but the thing is that both should be perpendicular. So here, let us see here. Here, let us see that this is a rod, and this rod is being pulled by a force F. So there is a change in a length, that is del L, and its original length was this. Okay. So now you can imagine that, and the area of cross section is your A. Now, if you imagine that young modulus of elasticity is your normal stress by longitudinal stress, so what is the values of normal stress? That is your force by area. Okay, and what is the value of longitudinal strain? So this is your change in length by original length only. So here our change in a length is del L only, because this portion is being changed by original length. So finally you will get that young modulus of elasticity is equal to L by A into del L. Okay. So elasticity is proportional to the young modulus elasticity. The more the young modulus value is, the more it has elasticity. And the unit, I have talked about unit. Unit is your Newton per meter square, because normal stress is what unit is Newton per meter square, and longitudinal strain has no unit at all, right? If it has no unit at all, so our final unit will be Newton per meter square. Okay. So I hope you have understood now young modulus of elasticity. It is just a constant for a material, right? Okay. Not shear. Now see here. Shear modulus for solid is less than. So I hope this slide is just up and down. So after this young modulus, we need to discuss about shear modulus. So this is a very important modulus, shear modulus. It is a type of elastic modulus. Modulus of elasticity, right? It is the ratio of shear stress to the corresponding shear strain. See, first of all, if you are applying a force tangentially on a surface, and this surface is being fixed here, right? So what will happen? There will be a change in an angle will happen, right? And see here, force and area both are tangential. See, area, it is just along the area, not perpendicular to the area. In normal stress, what we have discussed, area, see here, area and force both are perpendicular. Area and force are both are perpendicular. But what about shear stress? Shear, whenever we apply a force, see here, when we are applying a force, so it is just parallel to the area or acting tangentially. So as soon as you are applying a force, so what is happening? See, below it is your fixed point. It is not just movable. Okay, it is your fixed, right? So when you apply a force, so what will happen? There is a change in a shape at all. See here, dotted structure shows you the change after shape. So there is a change in angle, and this angle is known as shear modulus. This angle is known as shear strain. So shear modulus is basically the ratio of shear stress to the shear strain. For more, if you want to go for more details, so please go and visit our part 1 video, so that you will able to understand shear stress and shear strain more clearly. So what is the value of shear stress? So that is a force by area, right? And what is the shear strain? So that is phi. Phi, you know that how to find phi. Phi is equal to x by L. So I don't want to discuss once more here. So please go that video. So here finally we are getting the value, that is G is equal to F L by AX, where G, it is also known as modulus of rigidity. It is also known as modulus of rigidity or shear modulus, whatever you want. And the unit will be same at all, because it is all we are talking about modulus of elasticity, and the unit of modulus of elasticity is your Newton per meter square. Okay. So you have understood now shear. Shearing means what? When a force is acting tangentially to any of the surface. See here. So this type of things will happen in shear. So now shear modulus. Shear modulus for solid is less than the Young modulus. So you know that every solid has a shear as well as Young modulus. So when you are applying a force like this, then the modulus of elasticity will be Young modulus. But as soon as you will apply a force like this, and the area is of cross section is this only, so both are parallel. So what will happen? it will be a modulus of rigidity. So G is always less than young modulus of elasticity, and for a most of the solid the relation must be, remember, G is equal to young modulus of elasticity divided by 3, right? G is the only characteristics of a solid as a gas and a fluid does not have fixed shape. See, G is the only characteristics of the solid but not for the gas and a fluid. So I hope you have understood this shear modulus. Okay. Now I am talking about a bulk modulus of elasticity. Okay. See here, same thing, normal stress by volumetric strength. The thing is that in shear here, here it is defined as the ratio of normal stress to the volumetric strain. Here volume is changed. Suppose there is a sphere. As you are applying a force or pressure from all the sides, so what will happen? What will happen? Suppose you are applying a pressure like this. So what will happen? Its size will decrease. So earlier its size was V, and after applying a force, so it become V minus del V. So normal stress is your F by A, and volumetric strain, I have already discussed this thing. Volumetric distance is here minus del V by V. It is negative because volume get reduced. See here, volume get reduced. If it is positive, then we have to use positive. And P is the pressure applied from the outside. So pressure is equal to force by area only. So normal stress is what? Force by area, and del V by V is your volumetric strength. So force by area we can write here pressure. So pressure into V will come up, and this will be del V. Okay. So this is what bulk modulus all about. Bulk modulus. In bulk modulus, you should remember that we are talking about volumetric strain, but in shear modulus we are talking about the angle, change in angle. But as soon as we are talking about young modulus, we are talking about change in a length. So length related to young modulus. See, if I will talk about length, so length is related to young modulus of elasticity, modulus of elasticity, and angle phi, that is related to G. Okay, that is modulus of rigidity, modulus of rigidity. And if I am talking about bulk model, that is volume, change in a volume, so we are talking about bulk modulus of elasticity, bulk modulus of elasticity. Okay. So here this is your bulk modulus. The value of a bulk modulus of elasticity is maximum for a solid and minimum for gas. So this is very important. So bulk modulus of elasticity is maximum for solid and minimum for gas. So you should remember this. So I hope you have got clear each and every topic. You go through this, the notes I have also provided, class notes in the link description below, so that you can go through that, and you will able to reach out each and everything. Okay, if you have any query, please feel free to comment in the given below comment section, so that I can rectify your problem. You can personally contact our institutes also for any doubts. Okay, thank you everyone. Thank you for today's class and watching video. Thank you everyone.